All right, we're shifting gears a little bit here now. This entire unit so far has assumed that light is a wave. From the very first day, we talked about EMR being a wave. We talked about it being an electric field wave, a magnetic field wave, perpendicular to each other. We talked about these four properties of waves that are exhibited by electromagnetic radiation. There was overwhelming evidence to support that light was a wave. But fast forward to 1887, there was an experiment that was performed by a guy named Heinrich Hertz called a photoelectric effect experiment. We'll talk about that a little bit more in about 10 minutes. But basically, that photoelectric effect experiment discounted the wave theory of light. It said something's wrong with this wave theory of light. Something doesn't quite work out. So along comes Einstein in 1905, who comes up with a theory called photon theory. Einstein in 1905 said that light is a particle. Now, he's not saying that it's not a wave. Can you notice I didn't say light's not a wave, it's a particle. Einstein said light's a particle. So what he's basically saying is that, look, it's still got this wave nature that was supported by all this evidence prior to 1905, but it's got a particle nature as well. Light exists as both a particle and a wave. It's got a wave-particle duality, we call it. It is a wave. It exhibits refraction, diffraction, interference, polarization, but it also exhibits properties of particles. Einstein said that a particle of light is called a photon. He named a particle of light, a little chunk of light, like a little rock. If you throw a rock, okay, that's what we mean, a little pebble of light, a rock of light. He called it a photon. Now, a better definition for this photon, a more scientific definition for this photon than a particle of light is a quantum of energy or a bundle of energy. So basically what Einstein's saying is that, look, you throw a rock, it's got a certain amount of kinetic energy. Okay, this photon or this particle of light is also characterized by a certain amount of energy as well. Except it's not kinetic energy because it doesn't have any mass. The energy of this photon, rather than being equal to 1/2 mv squared, would be equal to h times f. F stands for, you guys know this, F stands for what? The energy of the photon is equal to a number h times, F stands for, sorry, no, not the focal length, the frequency of the light. So Einstein's saying that energy of the light is related to the frequency of the light. Now, if you go back to the first day of this unit, we talked about the spectrum, right? Radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, and gamma rays. And we listed the frequency range of this, and this. Okay? And from the frequency range of these three things, we could determine if a particular frequency that we were given, what type of light it was. We could also determine a particular wavelength, what type it was, by using the equation F is equal to V over lambda, converting it to frequency. And I told you you could also determine if you were given a certain energy of light, what kind of EMR it was. Well, you'd use this equation to solve for frequency based on the energy of the light, calculate the frequency, and then compare it to the frequency ranges that you remember. So the energy of the light is related to the frequency. The higher the frequency, the higher the energy. E is equal to h times f. What does h stand for, though? It's a constant. It's a constant that we call Planck's constant. This guy named Max Planck better be given some credit, at least here. Einstein came up with this idea of photon theory, the particle of light. But Planck was the first guy to really come up with the idea of bundles of energy, the idea of discrete energy levels. Okay, the first guy to really introduce quantum theory. Now, he didn't introduce the idea of particles of light. So we're going to give most of the credit to Einstein here. But this guy Planck, who came up with the idea of levels of energy, has to be at least given some credit. Okay, so we name a constant after him. What's the value of his constant? 6.63 times 10 to the minus 34. Not joules per second, joules times seconds. Oh, wait. It's also 4.14 times 10 to the negative 15 electron volt times seconds. How can it be two different values? How can a constant, how can we name something a constant, yet it have two different values? What's the speed limit on the highway out there? Highway 2. What's the speed limit on 2A? Just after we leave the school, go out to 2A there by the car dealerships. What's the speed limit out there as you're going out to Highway 2? 100 kilometers per hour? Most of you would have said 100 kilometers per hour. There might have been one or two of you that thought you were going to be really, really smart about this and said, it's about 27.7 meters per second. Well, you're both right. Even though that's two different numbers, you're both right because they both mean exactly the same thing, right? Well, if you can have a speed limit that is both 100 kilometers per hour and 27.7 meters per second, then why can't you have a constant that's both 6.63 times 10 to the minus 34 joule seconds and 4.14 times 10 to the negative 15 electron volt seconds? It's two different units. That's it. Same number. It's just two different units, just like kilometers per hour and meters per second are two different units. Make sense? Okay, over the next couple of days, we're going to do quite a bit of work with this photon theory in the context of the photoelectric effect. But before we introduce that photoelectric effect, the thing that really prompted all this to happen, okay, we're going to spend just a couple of questions spend a little bit of time working on a couple of questions involving just photons, okay, outside of the context of the slightly more difficult and involved photoelectric effect. So the first question here, how much energy is carried by a photon of red light with a wavelength of 600 nanometers? Straightforward question, really straightforward question. Okay, we got a unit there that we don't like, but other than that, pretty easy. We only have one equation for energy, right? E is equal to h times f. But wait a second. Maybe this isn't so straightforward. We're given wavelength here. Any ideas? Yeah. Good, excellent. V is equal to f times lambda, or f is equal to v over lambda. Now, when we're talking about the speed of light, Daniel, we usually call v c. So we'll say f is equal to c over lambda. But it's the same thing, right? So if we replace f with c over lambda, the equation becomes hc over lambda. Take a look on your data sheet for a second. You should see on your data sheet an equation that says E is equal to hf equals hc over lambda. They give you both of those equations. So what Daniel just did, because I hadn't told you about it, they actually do it for you. Okay. It's good, though, that we understand where that comes from. Well, which part are we going to use? Not the hf part, rather we're going to use the hc over lambda part. Now, which value of Planck's constant do you want to use? I don't care. Use whichever one you want. But I'm going to use 6.63 times 10 to the minus 34 joules seconds times 3 times 10 to the 8 divided by 600 times 10 to the minus 9. I'm going to get a value for energy. I don't know what that is. But the value for energy I get is going to be measured in joules. Had I decided to use the 4.14 value times 10 to the minus 15 electron volt seconds times 3 times 10 to the 8 divided by 600 times 10 to the minus 9, this is equally as valid. But the answer I would have got would have been in electron volts. It just would have been two different units that describe energy. So, now, if on a test they specify what units they want the answer to be in, then, all right, use the constant that goes with that. But if they don't specify, use whichever one you want. Joules or electron volts. There's no right answer. I shouldn't say that. They're both right answers. There's no wrong answer here. Okay. I'm going to give you just a minute to work on first work on these questions here. Okay, it might not give you a chance to finish all three of them, even though they go quite quickly, because I want to get at least a couple more examples in here, okay? But take some time right now to at least get the first question or two done here. Okay, let's take a quick peek at number 3. Daniel, this goes back to unit 2, right? Our energy unit. Sorry, not our energy unit, our electricity unit. We want to convert electron volts to joules. Basically, we're just going to say 1 electron volt equals 1.6 times 10 to the minus 19 joules. That conversion factor is on your data sheet, right? 15 electron volt equals X joules. So we're going to turn around, take that up, X ends up being equal to 15 times 1.6 times 10 to the minus 19. Make sense? It's been a while since we've done that, right? So sometimes you just have to refresh your memory. Okay, let's take a look at this example. A little bit harder. Okay, a little bit harder on this example. It says, your eye can detect as few as 500 photons of light. The eye is most sensitive to light, having a wavelength of 510 nanometers. What's the minimum amount of light energy that your eye can detect? Let's get the energy of a photon here first. The energy of one photon is hc over lambda. It's also h times f, but since we're given the wavelength here, let's use this equation, hc over lambda. Okay, let's use the energy, the joules value here, 6.63 times 10 to the minus 34 joule seconds. You could use the 4.14 value. Okay, I'm telling you what though, guys. If in doubt, go with joule seconds. Go with the 6.64. If you're not sure which one you should use, go with the joules one. There's going to be a couple of times later on when you can't use the other one, and I'll explain when that is, when it happens. Okay, but you can always use the joules one, the 6.63 value. So if in doubt, go with it. Let's get the energy of that photon. We get 3.9 times 10 to the minus 19 joules. All right, is that it? Is that our answer? No, that's the energy of one photon. What do we got to do to find out how much energy our eye needs to have in order to detect this light? It's 500 photons, right? But how much energy is that? What are we going to do to get that? Right, multiply that by 500. Okay, take that number, multiply it by 500. We end up getting 1.95 times 10 to the minus 16. So there you go. That's how much energy our eye needs to receive in order to actually physically see something, in order to have our, whatever it is, I'm not a biologist, but whatever it is in our eye that needs to be activated needs to have that much energy. All right? I'm going to do another example here just so we make sure we have enough time here. How many photons are emitted each second? Oh, wait, each second by a laser pointer that has a power output of 0.4 milliwatts. The average wavelength produced is 600 nanometers. I don't know about you guys. You see this question, though, and it seems to me that we might be at a little bit of a loss as to how we're going to get an answer here. Seems like a tough question. What do I always say, though? Okay. Start with something you know. Everybody's got a place to start here. Everybody has a place to start here. Simon, where do you want to start on this? Let's assume, maybe you know how to do this question. Okay, if you do, that's great. But let's assume for a second that you don't know how to do this question. Where are you going to start? Perfect. HF or HC over lambda. Good. Okay. We don't necessarily know how this is going to tie into getting us an answer, but it's something. So let's do it. Okay, easy, go to HC over lambda, 6.63 times 10 to the minus 34 joules seconds, times 3 times 10 to the 8th, the speed of light, divided by 600 times 10 to the minus 9. We get 3.315 times 10 to the minus 19 joules. All right, so there's the energy of a photon. We're looking for a number of photons. Anyone? Something else? Yeah. Divided by 600. Divided by 400. Why 400? Why would you divide by 400? Not saying yes, no. I'm just asking why. let's at least go down that road. Let's change this into watts. Our power output here is 0.400 times 10 to the minus 3 watts, right? Or we could just move the decimal place over 3 places if you want. We can change that from watts to joules per second, though, right? Because a watt is a joule per second. Wait a second. Wait a second. How many photons are emitted each second? We have the energy each second, because power is joules per second. We have the energy per second. So Daniel, you said divide the two, right? You are going to divide the two. Okay, you're right. If we want the number of photons, then let's take the energy, the total energy that we have. Let's take the energy that we have in 1 second and divide it by the energy per photon. That'll give us the number of photons. So basically, the total energy in 1 second, except it's not going to be 400, Daniel, it's the other way around. We're moving decimal points the other way around. But you had the right idea there. 0.400 times 10 to the minus 3, that's the number of joules total that we have in 1 second. Okay, the energy for 1 photon is 3.315 times 10 to the minus 19 joules. I don't know what that works out to be, but that's going to give us the number of photons, right? Remember we said earlier on this year, we said you want to find a number, take a total and divide it by the amount for 1. Okay, that's what Daniel did. He took a total energy in 1 second and divided by the amount of energy for 1 photon. Except last time we did something like this, it was total charge divided by the charge for 1 electron. Here it's the total energy divided by the energy for 1 photon in 1 second. Anybody else have that same thought, or was it just Daniel the genius here? Daniel, just you? Good. Guys, that's a tricky question. Okay, that's a tricky question. Okay, all of you guys, I think would have been able to start right there. E is equal to hc over lambda. But not all of you were able to go to that next step. Okay, that was a big transition there. Okay, there are going to be questions that maybe we can't do. We're not going to get 100 on this exam. That's okay. But at least if we have a place to start, it gives us a fighting chance. And maybe some of you, like Daniel was in that last question, are going to be able to come up with something that leads you to an answer there. Okay, does that make sense? All right, we got some questions to go along with that one as well, page 708. Remember, these are involving power. So again, big deal with this. Remember that 10 watts power, a watt is a joule per second. Okay, does that make sense? All right, you can work on those questions here now. Questions on page 708. We had the questions on page 707. And if you didn't finish these ones on 706, do those as well. Okay? Which ones do you want me to leave up on the board here? 708. So three sets of them. But I think you're going to agree that all 3 sets of these are going to go relatively quickly for you.